Very good mic. So, as you heard, my name is Torbjörn Rium. I'm very pleased to be here today to be able to present you why higher application layers should actually know about software-defined optics. So I'm inheriting this presentation from Stefan, who is a business development director and have huge amount of experience in this area. So I will do my best to interpret his thinking and the messages he wanted to give to you today. And I hope this will be sufficient for you to understand where we are today and what we're going towards. So I was thinking a little bit about how to present this to you. Everybody remembers a story. So how do I start this story? Once upon a time is a fairy tale, right? And this is no fairy tale any longer. Maybe a few years ago you could have started. Once upon a time we had, oh. But today this is getting close to reality. So I wanted to start this story by giving you a picture. What am I talking about? What are the stuff that you call big fat pipes? What's the components behind these big fat pipes? And how can we utilize dynamics in this environment to give you and your end customers better service? Right. So this is a picture I found on Netnod's homepage. I'm not really sure what this service is. If I can find a pointer. These are the big fat pipes I'm talking about. In your schemas or your applications, when you're trying to picture what is, we have two endpoints needing communication, and they usually are just a white line. What is actually behind these white lines? That's what we're going to talk to about today. So, to do this, I will try to cover this in 2 steps. First, we will talk about the advances in technology that enables us to have to enable this dynamics in the optical layer, which previously has not been so easily achievable. And then, secondly, we need to tie this up into some kind of bag. How do we use this then for our benefits? Okay. So first, advances in optical communications. So this is a traditional optical layer. What has, we can see on the right hand side, we can see a sort of a network of nodes, very well defined. We have endpoints, we have a meshed network. Communication could be between any of these points to any of the other points. However, we have been using a very strict optical spectrum. Each channel has been 50 gigahertz, 100 gigahertz, or whatever gigahertz. And it's split evenly over the spectrum to give us 40, 16, 80, a number of channels. But that's it. It has been fixed like this. On the optical layer, we have had limited reconfiguration possibilities. It has always been meant that you had to send somebody out there to really do some reconfiguration, the plumbing. we had to send somebody out there. The system itself was sort of stupid and only did what we told it to do. The interfaces on the end sides here, they have been using fixed data rates, not enabled to really be changed on the run. They're using fixed modulation. I'm not done yet. Fixed modulation schemes and fixed the FEC, the code that actually corrects potential bit errors going through the network. So what all of this stuff has resulted in is that we have a permanent connection. Once we have identified a need going to communicate between site A and site B, we have sat down with some planners, do the manual configuration of all the components needed for this, and set up the service, and it will remain the same until you say, we don't need this anymore, and you free up the resources. But this will change going forward. So to give you some background, what happens when you have a bunch of data coming from the router on the right-hand side? It enters a terminal component that translates the gray data bits to something colored and being able to be transported over the DWM layer. What happens then after it leaves the transponder unit in this side? This terminal could actually be integrated into the router as well. Yes, so it leaves the terminal. It's very well defined. You can see that it's sharp and crisp, and it's very easily to decide if it's a 1 or 0. And once it goes over the optical layer, sometimes you will go extensive distances, and the signal will be attenuated. It will be muffled by the glass. It's not perfect, so over time the power of the optical signal will degrade, and you will need to amplify it. So depending on how long the stretch between the endpoints are, you will need to amplify it 1 or 2 or many times. And for each step, as these components are not perfect either, the signal will be muffled. It will be mixed up with stuff we don't want, noise. And this is depicted by, as you can see, the signal is very crisp in the beginning, but after it passes each amplifier step, it gets more fuzzy, less possible to detect. And the trick is, of course, to reach this endpoint with enough clarity of the signal to be able to detect if it's a 1 or 0 in the end. Sorry, I will just get some water. Okay, now I'm ready again. So in the end, so the signal degrades, it will be more noisy in the end. In addition, we can encode more bits into each symbol we transport. So as you can see, we can use higher order of modulation schemes, which enables us to send more data per symbol, which in the end translates to higher bit rate per lambda. But of course, you can see, depending on which modulation schemes we're using, its complexity grows. And if you then combine the modulation scheme and the complexity of it together with the OSNR, you can see that it's a trade-off. Higher modulation scheme, higher bit rate, lower distance, right? You can't use as many amplifiers because the noise will be in this situation will be more significant than if you use a simpler modulation scheme. Okay. Then, this could seem a little bit complicated, but bear with me, I will try to guide you through it. These enhancement of the optical signal, which traditionally was just Morse code, like on-off, light on, light off, has now come to a place or a more advanced state, which we call coherent. It means that we're not just using the light on, light off to detect what kind of data we're transporting. We're using more advanced detection methods. And in that, okay. So then we can delve down. What does this coherent modulation options give us? Well, in the end, as I said, it's a trade-off. It will be a trade-off. But it will enable us to give us the best possible transmission characteristics that we give the resources for, or make the resources available to. Of course, it will enable us, if we such want, I mean, in the end, it will be a lower cost per bit, as we can use a decisive number of resources in the optical layer to enable this transport. Or if we have a really high need for high capacity, then of course we could use more resources in the network and enable us to give us a better density of the transmission, but maybe not so much reach and the reach. And then of course in the prolongation of that, it will be a higher cost to implement the service, but that is a cost we could live with as we need the higher capacity. So if you look at this one, we stick to this 200 gig per channel. You can see that depending on which modulation scheme we're using, if you're using QPSK, 8 QAM or 16 QAM, we will encode different amount of bits per symbol. But the trade-off here, you can see that we are able to achieve 200 gigabit per wavelength. But depending on which modulation scheme we use, we will use different amounts of the spectrum. And then if you have a need for 300 gigabit, you can see that we will need to use another set of modulation schemes, but we can, in a similar way, tweak the signal to our needs. Do we need to save spectrum to squeeze in as much channels as possible in the spectrum with long reach? We need to use a higher modulation scheme, but then the reach, of course, will go down. If you use a more spectrum per service, then we will have a longer reach of our system. We could turn this around. And now we have on the x-axis the nominal bit rate, and on the y-axis we have the reach. So in a similar manner, we can then see we have different modulation schemes. The QPSK is not fitting into this picture, it's above here. But to keep this nice and neat, we concentrate on the 4 higher ones. So then in this picture we can then look at, okay, we have a 16 QAM 200 gig wavelength. This could actually, with the same modulation scheme, be upgraded to 300 gigabit per second at the cost of, in this end you can see a narrow channel, and this one is a wider channel. So you can then deciding how depending on how much bandwidth you have per channel, or allowing the channel to use, you can come up to even 400 gigabit, but using then 75 gigahertz of spectrum. Or you can achieve 200 gigabit, but only using 37.5 gigahertz. So, why is this then important? These achievements that we have reached. Of course, in addition to the transponders that I'm talking about, the endpoints talking to the optical layer itself, of course, needs to be upgraded. I will not cover exactly how this is done, but of course they will need to go hand in hand and be also upgraded and being able to handle these variations of the optical signals, the optical carriers going through the network. So here we can see an example. We have a router, I'm trying to point. A router in Gothenburg and a router in Stockholm. We have optical layer in between. We have originally planned a 300 gigabit service going through this. And we have enabled optical restoration in this optical layer. We have told it, well, these are the nodes you have available, the whole thing. We need to get a service from Stockholm to Gothenburg with the X number of gigabit. And you're allowed to use other resources if something happens to the network. And in this case, somebody digs the fiber off. So then the optical layer itself will, okay, something has happened. It detects something has happened. It reacts and it says, okay, I can reach Stockholm, but we'll need to go through Malmö. And in this case, of course, the distance that this signal has to travel is a lot longer. Not going directly to Stockholm, but it has to go down to Malmö and then up again. So the restored path with the given resources are only allowing 200 gigabit. So the system, of course, can react and give the routers 200 gigabit. However, when we start to look at this type of events and flows and dynamics in the optical layer and transponders and its components, of course, this is not optimal. I mean, we have a service here that is thinking, I'm going to get 300 gigabit no matter what. So this requires communication. Christian Larsen talked about communication yesterday. I thought it was interesting because it touches this a little bit. Of course, it's not any code and stuff like that. I cannot go into that detail, but it's all about communication. The optical layer, it feels happy. It has restored the service, give to the extent what it's allowed, given the resources it has, and says, wow, I'm done. The routers are semi-happy. They have a service up, but not what it expects. And of course, above this, we have some functions or some customer wanting their applications to run, and maybe they have written their applications to depend on the 300 gigabit, but it doesn't really understand why it doesn't get it. So communication will be needed. And I will come to that in the second part. So, wrap up the technology. I'm getting a little bit short of time. This is what we have traditionally had. Very rigid, not dynamic optical layers. Given all the technology advances, we are getting there. We have transponders and the optical layer that can react on unforeseen events like rerouting, and given that we give them the rules and limitations between what it's allowed to do, it can react on its own. So how do we then use this in a wider sense? Yes, of course, we will need to have some kind of management system on top. This is normally depicted by this. So this is a very generic picture depicting a hierarchical multi-domain SDN architecture. So SDN is a very hyped word, but it's a software-defined network. So in this case, we have on top, we have a requirement. I need a 100 gigabit service between A and B. It should be encrypted, it should be whatever you can think. Below this, as this system doesn't know how the transponders from vendor A is working, the optical layer from vendor B is working, or how the door alarm handles in domain C is working. So I don't know how that should be relevant, but this depicts different parts of the network that could be relevant for the service. And to be able to not have all the intelligence in one system, so traditionally in an optical layer, we said that everything needs to be delivered by vendor B from starting point to end point. But in this type of new network, we're dividing up the resources so that you will be able to select transponders from one vendor, optical layer from another vendor, and cherry pick the configuration that you require. The network elements in domain B will report, these are the resources I have. The domain controller for these network elements will communicate with the SDN controller or orchestrator, depicting or informing the orchestrator, these are the resources you have to use, that are available for your use to create whatever your master is deciding that you should create. So this is normally what I wanted to wrap up. So this is the traditional telecom network, building an optical layer with a network management system reporting to some NOC or whatever the problems it has, but it doesn't really allow the top levels to do anything with the network elements. In this scenario, this network management will say, these are the resources you have available, these are the resources you can use to create whatever these guys want. So this could be a fairy tale, but we are closer to the reality than you can think. In the OFC 2019, we had a demonstration of this using entity communication and Telefonica operator OSS, BSS. which was telling the open source ONOS orchestration software how to that it needed to create a service from here down here. In this case, the Nokia transponders doesn't seem that they have their own NMS, but they are configured directly from the orchestration layer. But in the case of the optical OLS vendor, we had our own controller in between. So down here we can see the network elements, and these are network elements, of course, from the transponders. These communicate with the OLS controller, stating these are the resources you have available, and the OLS controller then talks to the orchestrator with transport API. So it delivers understandable language and predefined how to communicate and send requests to the optical layer. And in the same manner, the transponders are using a different protocol directly talking to the orchestration software, the ONOS. So, this is reality. This is coming. The stuff is there. Of course, there are different interests, different powers in the industry that says our way is the best way. So this ONOS is just one solution. There are many different ones out there. I use this slide just to show you that this is one possibility. Of course, you should investigate the other ones. What then are we going to achieve? What is the benefits of having an intelligent network able to resort its own problems, do the self-restoration, tweaking the services? What is the benefits? What are our benefits? Well, it's really up to us, right? We need to decide, how are we going to use these resources? How much intelligence, how much enforcement are we going to give? How much should we let the optical layer itself do its restoration and trying to achieve what we have told it to do? In the end of the day, we can use all this to tweak the communication paths in our networks, to be able to deliver bandwidth as a service, optical spectrum as a service. And in the end of the day, this will save dollars and cents for you. Thank you.
Time for one or two quick questions. Anyone has any questions for Torbjörn? Okay, please join me in thanking Torbjörn for his presentation. Thank you.
Thank you.